Let's consider one more example. So what we have here is a triangle. It's a standard problem, but let's discuss it. We have a triangle and we can define our x-axis this is the y-axis and this is the x-axis, and we have to find the center of mass of this object, and we know it should be somewhere in the meat of the triangle, and it's a two-dimensional problem. Okay, now we know that center of mass R is given as integral of rho, well, sigma, because sigma is the area density, or sigma is defined as mass divided by area of the object. In this case it's the triangle, and oh, I'm sorry, actually there should be an R here, and divided by sigma dA. Sigma is mass over area of the object. Now how to solve this? Well, you see, so we have R, this R, and we know this R will be somewhere here, something like this, and it will have an X component and will have a Y component, or let's call this capital X and capital Y. Now, as we have been doing all the time, we can break this vector problem into two scalar problems. That is, we can always break this vector R into two sets of system, and we can define it like this, that X is nothing but sigma X dA divided by sigma dA, and Y is nothing but sigma Y dA divided by sigma dA, right? Okay, so, well, you see, if you really write this properly, it should be like this. This is sort of symbolic, not really this, but it should be sigma X comma Y dA. This is what we mean by vectors. We have both the components present. That's it. And this you can break it like this. That's all. And they are perpendicular to each other, X and Y, so they don't really mess up with each other. So let's just calculate X, and similarly we can calculate Y, but let's try to calculate this thing. So we have a triangle, something like this. It's a right angle triangle. I should have mentioned it initially, but let's assume it right now. It's a right angle triangle, and then we have to find the center of mass. So let's see what should be dA. So let's choose a strip here which should act as dA for the X component. You see, this whole strip is at a constant length X from the origin, so all over the strip X is not changing, and here all we are worried about is the X, so we really don't have to worry about the Y part. I should have given more information. Let's say this is 1 meter, this is also 1 meter, and the mass is, well, mass really won't make any difference, but let's, for the sake of completeness, say the mass is 10 kilograms, right? Okay, so, and we know sigma is going to be the mass, which is 10 over A, but let's not worry about sigma right now. Let's call it just 10 over A. Okay, so X is going to be so let's calculate this, capital X. capital X is going to be sigma, which we already know is 10 over a. X, we already have chosen a variable, which is this small strip is a distance x from the origin, times dA. Now what is going to be dA? Well, you see, we have, whenever we choose a small differential element, we say this is dx in thickness. So our dx is changing along the x-axis because we are talking about the x-axis. So dA is going to be length of this small area element multiplied by the thickness of the small element. Now what is going to be the length of this element? We are treating this as a rectangle, a small rectangle. So element dA is going to be the length times dx, which is what is the area of a rectangle. So this is dx, but what is this length? Well, we can find this length using similarity or simple geometry, whatever way you want to use it. But I know the answer. The answer is the length of this string should be something like this. Let's call the length to be b. I mean the length is b. So I know that b over 1 should be equal to x x over 1. Makes sense? So b is same as x. So that gives me b is same as x. So what goes here is x, and divided by what is sigma? Again it's 10 over a, and dA again is this part, x dx. 10 over a gets cancelled. Anyway, sigma will always get cancelled if it's a constant. If sigma is a constant, we assume that density is same throughout, and it's not a problem. Sigma anyway gets cancelled, and m never plays any role. That's why I said m isn't. It's not really required to give the value of m. Okay, so sigma gets cancelled, but if sigma is changing over x and y, then we really can't do that. Okay, so this gets cancelled, and we are left with, now apply the limits. The limits are 0 to 1 divided x square dx divided by 0 to 1 x dx, and that should give us, well, let me do it fast in my mind, and it should be 1 over 3 divided by 1 over 2, and that gives me 2 over 3 meters. So x is 2 over 3 meters. And similarly, you can choose a y element. How will you choose a y element when you try to solve this part? Then you'll choose y like this, because on this area element y is not changing, and then you will actually, I believe you'll find the same answer, because there's a symmetry in the system. So I think y should also be 2 over 3. So somewhere here is going to be somewhere 2 over 3, and then 2 over 3 on the y-axis also. So there's a lot of calculus in this. It's just calculus actually. Starting from here is just calculus. Use calculus and find the value of center of mass.